Good morning, gang. What is this? Oh, okay. All right. So today, as promised, we're going to continue talking about volumes. I'm going to do some work to compare and contrast the methods. First thing I'd like to do, well, I guess that's not quite the first thing. So let's do the other first thing first. Let's get Q camera fired up. Oh, the screen share. Oh, yeah. All right. You do need this. At this point, I'm pretty sure we all know where we are, what this is, probably even the date. Today, a few things. First, a warning. If you've been using the temporary access for WebAssign, if you've not yet paid for a WebAssign access code, that's just about to boot you out. I got emails the other day asking me to remind you guys. I'm grateful for those. Unfortunately, they didn't tell me like the exact time or even the date, which was frustrating. It just said that, that the temporary access was about to end. So I'm not sure at exactly what moment you'll be booted out. But if you have not paid for your WebAssign access code, please do so. Okay, so if you're using WebAssign's free trial or temporary access, that is about to end. And you really want to get that code before they kick you out, because if they kick you out, there's going to be this like chain of things that has to happen. That chain of things usually takes a few days. And during those few days, you won't be able to work on homework assignments. So you can imagine how unpleasant that would be at this point in the semester where we're just starting to pick up speed. If you get kicked out of the class online and you're unable to get in there and work on things, it's going to hurt. It'll take a couple days sometimes to get back in. Like if you rush to the bookstore after getting kicked out and the bookstore happens to be out of those little packets with the access code, then you might have to wait for more to ship in, and then you have to get in there and log in, and like it can just be trouble. So please don't let that happen. Figure out the access code stuff today. All right, get that stuff figured out today. And then we don't have to go through any of that unpleasant business of like, oh, I got removed. Can we extend the access while we're waiting for the access code to come in? All that stuff is a pain, and the biggest problem is that you'll fall behind. This is not a time when you want to be unable to work on the stuff. You really, really need to be on top of it right now, because this is the part of the semester where, you know, we're ramping up. So I wish I had better information for you. I wish they'd told me exactly what time it was going to happen so you could budget your time a little bit better. If you're having a difficult time getting an access code, either you're having a hard time finding one, or you're having a hard time affording one, reach out to me and I'll see what we can do. Sometimes the department has a few access codes that can be given out to students in financial hardship. And sometimes if there's, one place is out, like the bookstore doesn't have it or somewhere doesn't have it, arrangements can be made to help you get it through other places. I know, of course, you can buy it direct from Cengage, but there are other options too. So please, if this is a problem that you're nervous about how you're going to solve, reach out to me for some help and I'll help you. But let's get it solved. Let's not let this sit. Another little announcement-y thing, check out the modules in Canvas. I updated the 6.2/6.3 module yesterday. So I'll go ahead and show you really quickly. Of course, I won't take time to go through the whole thing, but I'll show you really quickly what I added. So of course, the review material module, this is good. This is all sorts of stuff. If you had a Calc 1 class that ended a little too soon, didn't quite get to all the integral stuff it should have, didn't get to talk about U sub, you need a little brush up on your trig, any of that, right? All that stuff is here. Polynomial long division. This is going to be important when we get to section 7.4. For some reason, a lot of people forget this, but all this good stuff. Then there's this stuff, right? Most of this stuff has been here for a long time. There's the Paul's Online Math Notes page, which is really good. So if you've been having a difficult time with this, check out Paul. He is awesome. But I found something yesterday. Remember, we were searching for some GIFs, some animations to help you guys visualize things. The resource that I especially liked is apparently gone. That guy's website went down, but I found something new. I don't know why it's embedding here instead of straight to YouTube. So I don't want to watch this whole thing, but I do want to show you just a little bit. This is cylindrical shells. Let me start with the disc washer one. We should have a pretty good idea of what's going on with discs and washers by now. So he does the normal thing, but this is very nice. So he'll show you, he's got this bit of software where you can watch the region with the strip, and then he rotates just the strip, exactly like we say, and that generates the washer. I'm gonna turn him down. So you can watch this video, and I think you'll enjoy it a lot. It'll also help you see how the connection between the washers and the little differential solids we're using and the overall solid. So I'll let this play just for a minute so you guys can see, because I think it is really useful. We visualize the solid as being made up of a bunch of those washers by rotating a bunch of those little strips. Pretty cool stuff, right? So I'll show you just that. That's really the good shot. I'll show you that just one more time. Rotating just one strip gives us that. If we rotate all the strips at once, we get the solid, or something very close to the solid. And of course, when you integrate, you're going from that Riemann sum sort of thing to the smooth thing. So the integral gives you the volume of the smooth solid. He has one of these for the cylindrical shells method also. So here the strip is parallel to the axis of rotation because he's going to rotate about the y-axis. And you see rotating just the one strip gives you this cylindrical shell. Cool stuff. And then he'll drop in a whole bunch of those little strips and rotate all of them at once. And you get the whole solid. Or something very close to the whole solid, like a Riemann sum for the solid. And then when you integrate, you actually get the smooth thing. Very cool, right? So I haven't looked up what software that is. Maybe one of you, if you want to, or you, of course, would be welcome to do that. It kind of looks like it might even be free software. It does not look like it's especially sophisticated stuff. But this is what I was able to find the other day when I was looking for some visualizations, and I wanted to share those with you guys. So if you come to the modules here, that's again all I was wanting to do, is remind you that I've got lots of stuff here to help you out with the homework. So as you're getting stuck, if you want help seeing how things are going, if you want to watch someone do examples, that's what all the Patrick GMT videos are. You know, he just sits here and works problems for you. The Paul's online math notes are always like written descriptions with examples, definitions, and theorems. And then the two most recent added things are these two visualization videos down here at the bottom. So make use of these. I really encourage you guys to take a look at these. The textbook is good. Coming to class, of course, is essential. But if you're looking for a little bit of extra understanding, this module should be really helpful. What else was there announcement-wise? Of course, there's no class Monday. It's Labor Day. Day for us to celebrate the laborers of our world. It's a good thing. And I think that is it for announcements. So beyond this, today I just want to work some more shells problems with you. I want to help you understand how the shell method works, give you a little bit more of a feel for it. Before we do that, at the end of class last time, I promised that I would give you the formulas for the 3 different methods. So here they are. I don't recall. I think one of my sections I had time to actually show this, and one of them I didn't. So if yours was the section that I did not have time to show this, please go ahead and add this to your notes. So the slicing method, so what it is, each of these 3 formulas, slicing and disk washer, these are both from 6.2, and cylindrical shells, this is 6.3. These are the 3 methods we have for finding volumes of solids. The slicing method is what we use for solids that don't have rotational symmetry, solids that are not solids of revolution, solids that don't come from revolve this region about this line. So, you know, if I just give you a pyramid, say find the volume of this pyramid, or if I give you a torus and I say find the volume of this torus, it's a good example of a problem on which slicing works well. Here, our dV, the thing that we're going to end up integrating, is the cross-sectional area of your slice. So you poke an axis through your object, you imagine slicing it, you take a look at that cross-section, and then you find the area of that cross-section, multiply by the differential thickness, and I'm going to use dTs everywhere here. And dt could be dx or dy, depending on your situation. So dV, the thing you're going to integrate, is the area of your cross-section times dt. Right, where A of t is the area of a cross-section. So you slice, find the area of the cross-section, slap on a dx or a dy, and you integrate that. That's the slicing method. The real reason I do this is to help you contrast the 2 methods here, the disk washer and the cylindrical shells method. So in the disk washer method, from 6.2, you draw your region, your axis of rotation, and then you draw your strip perpendicular. Remember, this symbol means perpendicular. You draw your strip perpendicular to the axis of rotation. Okay, you must do this first. You sketch the region and then draw your strip in perpendicular to the axis of rotation. You imagine revolving just that strip. You'll get a little differential solid like we saw, the red solid in those videos, and it will have 2 radii, an outer radius and an inner radius. The outer radius is always, and this is how you need to think of it, think of this as the definition. So again, if you haven't written this down, please write this down. The outer radius is defined to be the distance from the far end of the strip to the axis of rotation. So because your strip is perpendicular to the axis of rotation, maybe here's my strip, here's my axis of rotation, because it's perpendicular, there will be a far end and a near end. The distance from the far end to the axis of rotation, that's always cap r. And little r is always the distance from the nearer end to the axis of rotation. Sometimes this is 0. right? If little r is 0, that means you're dealing with a disk rather than a washer. But it's the same method, and it has the same formula. Just if little r is 0, this goes away. So having drawn your region, drawn your strip, and identified these two distances, you then integrate this, which is the volume of the little washer. So dV, the little differential volume, is pi times cap r squared minus little r squared, and that's in parentheses, times either dx or dy, and again, it depends on your situation. But the big thing is dishwasher, strip is perpendicular to the axis of rotation, and then make sure you've got these definitions of r well understood. So again, I would write this down if you don't have this in your formula, in your notes somewhere. The cylindrical shells method, the method that we touched on for the first time Wednesday, and we're going to talk more about today. The main difference between disk washer and cylindrical shells is that here you draw your strip parallel to the axis of rotation. All right, here in disk washer, strip is perpendicular. Here in cylindrical shells, strip is parallel. That's what makes the two methods what they are. Since the strip is parallel to the axis of rotation, there's only one way to measure the distance from the strip to the axis of rotation. There is no near end or far end. The strip is very, very thin, so it's just the distance from the strip to the axis of rotation. That's the radius. And h is the height of the strip, or the length of the strip, however you want to think of it. And then you integrate dV, which is 2 pi r, that's the circumference of the cylindrical shell, times the height times either dx or dy. So I'll leave this here just for a minute so everybody can get it written down in case they haven't. And then we're going to jump into some more problems, and we can do whatever problems you guys would like. I suppose I do have one particular problem I would like to go through, but besides the one that I have in mind, why don't you go ahead and tell me in chat which of these volume problems you guys would like to see worked today? Yeah, out of the homework. And they can come from somewhere else if you're working on problems from somewhere else, if you're doing other problems from the textbook, or if you found other problems online you've been practicing with, I'd be happy to go through some of those. But I'm imagining most people are working on the homework. So if there's anything there that you've been struggling on or you especially want to work with, then let's look at those. Colin would like to look at number 12. We go tab over to the other side stuff. Number 6 and 12, certainly. Yeah, good, okay. So then let's start with number 5. It's interesting when the axis of rotation is not one of the coordinate axes, and it sounds like that's what you're talking about there, Griffin. Yeah, this is a good problem. Okay, so we'll start here. We'll do 5, 6, and 12 to get started, and then I'm going to shove one in of my own. So give me just write this down. Okay. Did I say 12? I think this is 5, right? Yeah, sorry. Yeah, we're going to start with 5. So I'll go in order. We'll do 5, 6, then 12. 5, 6, 9, 12. So we want to find the solid, find the volume of the solid generated by rotating the region about y equals 3. So I'm not writing all the words. We'll just get to the actual good stuff. So the curve they give us is 3 plus secant x. And they want us to take the region bounded by that curve and y equals 5 from negative pi over 3 to pi over 3 and rotate it about the line y equals 3. So 3 plus secant x, we remember from the area problems where we had to work with the graph of the secant function, what he looks like. Let's see, actually, I'm going to need to give myself a little bit more space. So let me do it like this. Let me call this here 3. So then 3 plus secant x, remember how the graph of secant looks. It comes down, it's got this like U-shaped thing that comes down to 1. So if I make this 3, then this would be 4, and 3 plus secant x will come down to a min there. I would think of it like this. The smallest secant ever gets is 1. So the smallest 3 plus secant x ever gets is 4. And then the line y equals 5. Let me exaggerate this a little bit, call this 5 up here. It'll look like that. And we want to rotate around y equals 3. Okay, so my art is a little worse right now than normal. Sorry, I'm still a little bit groggy, still waking up. But we can see it, right? Here's y equals 3. Here's y equals 5. Here's 3 plus secant x. We want to rotate this region about that axis. They tell us we're working from negative pi over 3 to pi over 3. And again, I suspect that they're just saving you the time of solving for these intersection points, just like in the previous problem. If you set 3 plus secant x equal to 5 to find those intersection points, that's the same as saying secant x equals 2. And that is at negative pi over 3 and pi over 3. So this guy right here, this is the point. Pi over 3 comma 5. And this point right here is negative pi over 3 comma 5. So in view of our discussion at the start of class, what should I do now that I've drawn my region? What's my next step? Before we find the two r's, what do we have to do? Yeah, the r's come from thinking about a strip. So we have to draw in the strip. So, okay, here's my strip. I'm using the disk washer method. So my strip goes in perpendicular to the axis of rotation. Axis of rotation is this horizontal line, so my strip will be vertical. And now I can go after my r's. Remember, little r is the distance from the near end of the strip to the axis of rotation. So if my axis of rotation is the line y equals 3, here's my strip. The near end of the strip to the axis of rotation, that's this distance. And the far end of the strip to the axis of rotation, that's this distance. So those two definitions for big R and little r, those are critical. Okay. So of course, I'm thinking of this strip as being at an arbitrary x value that I just call x, and the key to figuring these things out is to characterize this point on the curve, which is x, comma, what? What is the y coordinate right here along the curve y equals 3 plus secant x, whose x coordinate is x? Yeah, good. 3 plus secant x. So this point is x comma 3 plus secant x. So who can tell me what little r is? The vertical distance from this point to this axis. Good, secant x, right? It's not 1, it's not constant, it moves, right? If the strip is over here, then little r would be the distance from here to here. That's certainly larger than if the strip is right here. Then little r would be this distance. So little r is not constant, it definitely changes. So here's how we figure this out. Little r is the vertical distance from here to here. That means I need to take this y value minus this y value. The y value right here is 3 plus secant x. The y value right here, this point is x comma 3. So if I subtract those y values, I get 3 plus secant x minus 3, which is just secant x. Does everybody see how I'm finding the little r? Here's my axis of rotation. Here's the nearer end of my strip. So little r is this distance. The y value right here at the bottom of the strip, near end of the strip to the axis of rotation, is the y value along this curve. This curve is y equals 3 plus secant x. So the y value right here is 3 plus secant x. If I take the larger y value there and subtract the y value here to get this distance, then that's 3 plus secant x minus 3, which is just secant x. Yeah, I find that very helpful too, right? So what we want to do is imagine this strip as moving through this region, right? You can imagine it as starting way over here, and it moves through the region like this. So that little r is changing. Over here, the little r is larger than it is as we've drawn it, because the bottom of that strip is further from the axis of rotation. Right here, little r is as small as it ever gets, because that's as close as the bottom of that strip ever gets to that axis of rotation. And right there, just briefly, right here, r is equal to 1. But then it starts growing again as the bottom of that strip starts to retreat away from the axis of rotation. When we're up here, r is going to be larger again. Yeah, at these guys, r is 2. Right here at x equals 0, r is 1. And it varies depending on where the strip is. So you have to imagine this strip as moving through this region. So everybody see what Griffin's saying in chat? Those are good observations. Yeah, very good. And capital R is constant. The far end of the strip is always up here along the line y equals 5. And the axis of rotation is always right here at y equals 3. So no matter where the strip is, the distance from the far end of the strip to the axis of rotation doesn't change. If the strip is right there, or if the strip is right here, or if the strip is where I've drawn it. The distance from the far end of the strip to the axis of rotation is always 5 minus 3, which is 2. Is everybody comfy with where little r and big R came from and why they have the values they do? No doubt, this is what makes these problems hard. This is the hard part of this problem and every problem like this. Okay, from here, you can get away without even drawing the little differential solid if you want. I'm going to draw it just for the sake of completeness. Here's my little r. Here's my big R. And dv. This is, of course, dx. The thickness of that strip is pi times big R squared minus little r squared dx. Big R is 2, so big R squared is 4. So this is pi times 4 minus little r is secant x, so little r squared is secant squared x. And dx is dx. So this is our dv. And that means that v will be the integral of dv. But from where to where? So what x values do we have to allow that strip to run between in order to let that strip sweep through the whole region? Again, they've kind of helped us out here. They've told us that x is running from negative pi over 3 to pi over 3. The smallest x value anywhere in my region is over here at negative pi over 3. And the largest x value anywhere in my region is over here at positive pi over 3. So I have to integrate dv from negative pi over 3 to positive pi over 3. So that means I'm integrating pi. I'll pop out the pi from negative pi over 3 to pi over 3, integrating pi times 4 minus secant squared x dx. Thankfully, the antiderivative step here is really easy. The antiderivative for 4 is just 4x. What's an antiderivative for secant squared? Tangent, yeah. So this is pi times 4x minus the tangent of x, all evaluated from negative pi over 3 to positive pi over 3. There is symmetry here, so you could exploit symmetry and say this is an even function. So instead of integrating from negative pi over 3 to pi over 3, I'm going to go from 0 to pi over 3 and multiply by 2. But I'm just going to do this in the most natural way. But if you were on a test and you needed to save time, at this step you could have also observed that the symmetry of the function, the evenness of this function, will allow you to get away with that trick. But here we'll get pi times 4 times pi over 3 minus the tangent of pi over 3 minus 4 times negative pi over 3 minus the tangent of negative pi over 3. And there's a lot of minus signs that can get jumbled up here, so you want to be very careful. Tangent happens to be an odd function, so you could pop this minus sign out here, but then when you distribute this one, it'll become negative again. We'll just do it all very carefully. So this is pi times, here I've got 4 pi over 3 minus, what is the tangent of pi over 3? This we need to know from our unit circle. It's the sine of pi over 3 divided by the cosine of pi over 3. Which good is just the square root of 3. And then from that, we're going to subtract. And now I'll distribute my negative. Negative times negative 4 pi over 3 makes a positive 4 pi over 3. So I'll have plus 4 pi over 3. And then here I've got two negatives make a positive, and then the tangent of negative pi over 3 is negative root 3. So this will be minus, I'll write it as plus negative root 3 to help us see where everything comes from. So this piece right here, the tangent of negative pi over 3, that's negative square root of 3. And these two minuses here make this plus. But of course, adding a negative is the same as subtracting. So now I'll combine the similar things. The 4 pi over 3 plus 4 pi over 3 makes 8 pi over 3. I've got pi times 8 pi over 3. Minus root 3 is minus 2 copies of the square root of 3. And you could leave it like this, or you could distribute the pi. Either way is just fine with me. Questions on this problem? Yeah, Zach, nice typing of the square root notation there. Questions on how we came up with R, big R and little r? Everybody's nice and comfy. Okay. Okay, so that was 5. We wanted to look at 6, 9, and 12. So again, find the volume, blah, blah, blah. Y equals the natural log of 7x. Y equals 2, y equals 6, x equals 0, about the y-axis. And this is still 6.2, so this is still disk washer. The natural log of 7x. Well, that's going to look a lot like the natural log of x, except things are going to be, let's see, I might have done a bad job drawing that axis in. He'll be equal to 0 when x is equal to 1/7, because the natural log of 1 is 0, so I have to ask, when is this inside equal to 1? So I'm going to mark this as 1/7. And he'll be equal to 1 when x is equal to e over 7. So I'll mark this as e over 7. He still has that vertical asymptote at 0. Okay, so here's y equals ln of 7x. Another way you can think about how you get the graph of ln 7x from the graph of ln x is by compressing horizontally by a factor of 7, right? Because that's what multiplying on the inside by a constant does. It scales you horizontally. Now let me see. We have to get all the way up to y equals 2, all the way up to y equals 6 even. So I am going to have to redraw this. I haven't given myself enough space. And that happens a lot, right? Where you first start sketching and then you realize, oh, I need more space. So don't stress if that happens to you. It happens to me all the time. So let me give myself a lot more vertical space in the positive direction. Here's 1/7. I'll mark e over 7, but then we're going to need a lot more vertical space. At e over 7, we're up here at 1. This thing continues to grow, although slowly. Looking something like this. The lines y equals 2 and y equals 6. So I'll say 2 is like here. 6 would be way up here. X equals 0. Yeah, still not enough space. So this is a little bit awkward. Let's try uno más. We need to get all the way up to y equals 6. This very slow growing function. I may need to exaggerate the shape a little bit. I'll do it like that. Okay. So y equals 2 would then be down here. This is still 1/7, comma 0. I'm not even sure that's going to be relevant. We want to rotate about the y-axis. So between 2 and 6, this is my region. Ah, shit. All right. So here's the line y equals 6. Here's the line y equals 2. And the line x equals 0, that is the y-axis. So my region is this region. Okay. I know the challenge for me drawing this there, the reason it took me a few tries to get this scaled right, is because the natural log function grows so slowly. It's rare that you look far out enough so that the natural log is all the way up to 6. Especially when you scale it like that. But that's okay. This is good enough. So this is the curve y equals the ln of 7x. Here's y equals 6, here's y equals 2, here's x equals 0. So this is my region. Is everybody comfy with where this graph came from? I know I had to redraw it a few times, so I'll give you time to get caught up with me there. It's okay if you have to do that. Although I acknowledge that it is frustrating. So next I'm going to come in here and draw my strip. Since I'm using the methods of 6.2, the disc washer method, my strip will go perpendicular to the axis of rotation, which means my strip will look like this. Really putting my drawing skills to the test this morning. All right, so there's my strip. This is the x-axis. This is the y-axis. And those curves are what they're labeled as. Little r here is going to be 0 because the strip extends all the way to the axis of rotation. All right, here's the nearer end of the strip, and here is the axis of rotation. So the distance between the near end of the strip and the axis of rotation is 0. Big R, however, is not 0. Big R is the distance from the far end of the strip to the axis of rotation. That's this. And this point right here is x comma ln of 7x. So I would be tempted to say that this distance is just x. And that wouldn't necessarily be wrong. It's just that it's not everything we need. Because the thickness of this strip is a dy thickness, I have to write both of these as functions of y. Thankfully, little r is 0, so I don't have to stress about him. But I need to write this now as a function of y. So we're going to take this guy and solve him for x. That will let me recharacterize this point in terms of y. Will let me write this in terms of y. We've seen this a few times now. The way to solve an equation like this for x is to exponentiate on both sides. The e raised to the natural log of 7x, that's just 7x. And then you can divide both sides by 7. So that's e to the y over 7 equals x. In other words, this point right here, I could recharacterize as e to the y over 7 comma y. So this x coordinate is e to the y over 7. So capital R is e to the y over 7, because that's what x is along that curve. Can everybody see this? Let's start with little r. Any questions about why little r is 0? If I were to revolve just this strip about this axis, then I would get a solid disk with no gap in the middle. So little r is 0, or equivalently, little r is 0 because the distance between the near end of the strip and the axis of rotation is 0. No matter where in the region I draw this strip, the ass end of it is right up against the axis of rotation. So there is no gap. There is no distance from the near end of the strip to the axis of rotation. That distance is 0. Big R is the distance from the far end of the strip to the axis of rotation, and that's always going to be the x-coordinate along this curve. Wherever your strip is, that larger distance is whatever this x-coordinate is. And that x-coordinate is e to the y over 7. So now we're ready. I don't really have to draw dv here, but we can. Never hurts. All right, this is the little differential solid dv that we get from rotating just that strip. And its volume is pi times big R squared minus little r squared times dy. And again, that's why I use in the formula I gave you, that's why I put a dt here, because sometimes it'll be dy, sometimes it'll be dx. Big R is e to the y over 7. So this is e to the y over 7 squared. Little r is 0. And we can clean that up. E to the y over 7 squared is e to the y squared divided by 7 squared. E to the y squared is e to the 2y, and 7 squared is 49. So this is my dv. And I'll have to integrate that. V is the integral of dv. And this is the step where I encourage you to come back and think about your bounds. So from what y value to what y value must I allow this strip to sweep in order to cover this whole region? What is the smallest y value in my region, and what is the largest y value in my region? Yeah, good, from 2 to 6, right? Down here, y is equal to 2. Up here, despite my bad art, y is equal to 6. So this is going to be integrated from y equals 2 up to y equals 6. And what is it that we're integrating? We're integrating this. So that's the integral from 2 to 6. I can pop out the pi. And I've got e to the 2y over 49 dy. Yeah, good. Good answers in chat. The factor of 49 downstairs is constant. He can come out front also. So I'll have pi over 49 times the integral from 2 to 6 of e to the 2y dy. And this is another one of our little micro u subs, right? We don't even need to write it down if we're getting comfy enough. If you do write down the substitution here, do it correctly and change the bounds. But I know that an antiderivative for e to the 2y is e to the 2y over 2, or 1/2 e to the 2y. So I'm just going to jump to the antiderivative step there because it's not hard. I have pi over 49 out front. The antiderivative for e to the 2y is e to the 2y over 2. And I'll evaluate that between 2 and 6. The over 2 can pop out also. I'll get 98. So it'll be pi over 98 times e to the 2y evaluated between 2 and 6. So that'll be e to the 12 minus e to the 2. When I plug in the 6, I'll get e to the 2 times 6. That's e to the 12. And then I subtract what I get when I plug in the 2. That's e to the 2 times 2 is e to the 4. Sorry, I think I might have said that wrong first time. Yeah, e to the 12 minus e to the 4. Sorry. Okay. Questions on this one? So as you solve these, make sure you draw these pictures nice and big, give yourself lots of space to get in there and label things. Try to organize your work. You know, if I were coming in here and looking at this, I could see, oh, here's the drawing of dv, here's solving y equals ln 7x for x, here's where I figured out the r's and the dv, and then here's where I actually did the integral. And you can put the pieces together. It's relatively easy to follow. I encourage you to try and do your work something like this. Keep it organized on the page as much as you can.
Excuse me, sir.
Yes.
Okay, so why we cannot say equal from 2, I don't know, the second line, y equal to 2,
Mm-hmm.
this point, no, not the all, where the graph got the intersection.
I'm sorry, what was the question?
Yeah, I'm talking about the small space from the y-axis to the graph. Yeah, that point.
So you're interested in finding the coordinates of this point?
No, I said that, so why we cannot say r equal to that distance?
Oh, because it changes. So this strip moves, right? This strip you have to think of as moving throughout this region. Down here, when the strip is down here, r is equal to that distance. But when the strip is up here, r is equal to this distance. And in between, it changes, right?
Okay.
So
Yeah.
r changes as the strip moves. You have to think of this strip as moving through this region, right? So the size of r varies here depending on where we are. It's true that one of the values for capital R is down here. This is the smallest value for capital R. And the largest value for capital R is up here. But in between, it takes a bunch of other values also.
Okay.
Does that make sense? That's a good question. Did everybody hear what Hitanji asked? You know, why can't we say that this distance is cap R? This is one of the distances that cap R takes. If you were to come here, let's see, where did we say? Yeah, here. And plug in y equals 2, then that will give you this distance, right? That distance is e squared over 7. So that's the smallest value that r takes, but it's not the only value that r takes. Right. If you said that r is the constant e squared over 7, then you would really be finding the volume of the solid generated by rotating just this part of the region, right? If capital R was the constant, then you would just be getting the volume of this bit. Another way to think of it is if cap R was constant, then this object would be a cylinder. It wouldn't, the solid wouldn't have any curvy shape to it. But if you imagine rotating this whole region, it's clear that the top and bottom are flat, but the side is like curvy. So yeah, Griffin's answer, that's good there. It's true that if R was always that, then all of your strips would look like this. They would all have that length. And that's not reaching through the whole region. So you have to imagine the strip kind of sliding up and down through this region, growing or shrinking as is necessary to meet the boundary curves. Does that make sense? So there's something kind of sneaky that we're doing when we drop this strip in. You'll notice I always put the strip somewhere like in the middle of the region, never at the very top or bottom, never at one of the edges, because I'm imagining the strip as moving. And so the reason I always drop it somewhere in the middle is so I don't get tempted to do what you're describing there, Hitanji, which is a reasonable trap to fall into, but it is a trap, so you need to watch out for it. And I think one of the ways, the nice way to get away from that trap is to always draw your strip somewhere like in the middle of your region rather than out at the edge. Okay. So other questions on this? I don't want to move away too fast. All right, if there aren't other questions, then I am going to move to number 9. Okay, this is the one that we did in class yesterday. So here, instead of having just sine of x squared, they give you these two constants, a and b. But they tell you that a is 6 and b is 2. So let me go ahead and draw this, and then I'll switch back. So a times the sine of bx squared would be 6 times the sine of 2x squared. Rotated about, what are we rotating about here? The y-axis. Okay. So this is WebAssign's way of trying to add randomness to the problem that I used Wednesday to introduce the cylindrical shells method. So this is the square root of pi over 2, according to their picture, right? They said the square root of pi over b. And this max height here happens to be 6. You can note that. That's how a and b modify the problem. And I want to rotate this region about the y-axis. And the thing we observed on Wednesday is that if you try to set this up with the disk washer method by drawing your strip in like this, there is no nice way to find a formula for cap r and little r. Little r would be the distance from the near end of the strip to the axis of rotation, and cap r would be the distance from the far end of the strip to the axis of rotation. But since they're both being given by this curve, and there's no nice way to solve this for x, because the function is not 1-to-1, we can't do it. But what we can do is come in here and draw our strip parallel to the axis of rotation like this. So that's what I'm going to do. And again, I'm thinking of this strip as being very, very narrow. I've drawn it quite thick, but it's a differential thickness. If I were to revolve just that strip, then the solid I would get looks something like this. I'm going to do my best to make a decent drawing here for you guys because we're still getting used to this stuff. And there really should be another, yeah. Okay. So this is the cylindrical shell that I would get from rotating just this strip about this vertical axis. Right, like the strip, you can even think of seeing the strip as being like right here. And if I rotate just that strip, I'll get something that's shaped like this. So this is dx. And then remember, here's the trick, right? Some people just like to memorize the formulas for dv. That's why I give you those. But if you're having a trouble remembering the formula for dv, or if you want to really understand where the formula for dv comes from, you pretend like you have some very, very sharp scissors, and you can come in like this and cut right here, and then unroll this object. If I were to do that, I would get a very thin box. The thickness is still that differential thickness. My box would look like this. So this is dv as it's generated. And then we cut and unroll like this to figure out what the volume is. This height here, clearly I need. And this length here, clearly I need. That length is connected to this radius. If I cut this thing and unroll it, then this length is the circumference of this circle, which is 2 pi times the radius. Remember, that's how circles work. Their circumference is 2 pi r. And then we come up here and we have to figure out, well, what is h and what is r? So look at the formulas that I gave you at the start of class. Let's start with h. Just in terms of words, what is h? And don't worry about the algebra. Think about how I characterized it for you at the start of the class. Yeah, it's the height of the strip, right? If this strip wasn't sitting right on top of the x-axis, it might not be the y value. It could be a difference of y values, but it's always the height of the strip. So I like to come in here and label these things. And then what is r? It's the radius. And where does the radius of this cylindrical shell come from in this picture? It's the distance from what to what? In this particular instance, it will be the x value, but it's not always going to be the x value. Good, it's always the distance from the strip to the axis of rotation. That's the thing that's always true. So what you'll notice as you work these homeworks, it's clear that we've recognized some patterns, and that's awesome. But what you'll see is that some of those patterns hold and some of them don't. If I were to move my axis of rotation around, then this radius here would not always be x. if I slid my axis of rotation to the right, say I made my axis of rotation the line x equals -1, then r would be x plus 1. But in these instances, what you guys said in chat are correct. So r is always the distance from the axis of rotation to the strip, because we're using the shells method. H is always the height of the strip. So here, I'm on the graph y equals 6 times sine 2x squared. So this point is x comma 6 times the sine of 2x squared. So h is 6 times the sine of 2x squared, because that's the y value up here. And the y value down here at the bottom of the strip is 0, because it's on the x-axis. And similarly, r here, this horizontal distance, that's just equal to the x-coordinate of this point, because that's how far over from the y-axis we've moved. And since my axis of rotation is the y-axis, that horizontal distance, that's just x. So remember, r is always the distance from the axis of rotation to the parallel strip, because cylindrical shells method, and h is always the height of the strip, or the length of the strip. It's the long dimension of the strip. And here, that's this y value minus this y value. The y value down here is 0, so it's just 6 times the sine of 2x squared. So dv, and you could jump to this without any of the pictures if you wanted to. I wouldn't take off points for that. Just make sure you really understand where everything is coming from. I recommend drawing the pictures. dv is 2 pi r h times dx, because the thickness of my strip here is a dx thickness. That's 2 pi times x times 6 sine 2x squared dx. And the integral here is not terribly hard. V will be the integral of dv. And we need to look at our picture to determine the bounds. I'm going to go from over here. If I move my strip all the way to the left here and still stay in the region, then x is equal to 0. I move my strip all the way to the right side of the region, x is the square root of pi over 2. So I'll be integrating from 0 to the square root of pi over 2. And then I plug everything in. I would like to pop out my constants. I have a 2 pi and a 6, so I can pop out a 12 pi. And then I'll have the integral from 0 to square root of pi over 2 x times the sine of 2x squared dx. Now we looked at an integral like this on Wednesday. How do I solve this particular one? This one's a little bit different. We will once again need a substitution, but the substitution this time will be a little different than it was last time. What am I going to sub for here? I wouldn't call this a micro U sub. Yeah, so the micro subs are things like u equals 2x, u equals 5x, u equals 10x, where your new variable is a constant multiple of your old variable. Here I'm going to substitute for 2x squared. So this is not a constant multiple of x. So I would go ahead and write this one out. This one is a little bit more complicated because your differential is not constant. So I'm going to sub z equals, and I would again encourage you guys to start using a different variable. Z equals 2x squared, so dz is 4x dx And we need to change our bounds. When x is equal to 0, z is going to be 2 times 0 squared, which is 0 still. When x is equal to the square root of pi over 2, z is going to be 2 times that squared. Well, root pi over 2 squared is pi over 2, and 2 times pi over 2 is pi. So my new bounds are going to be 0 to pi. And then we can go ahead and do the integral. So I still have my 12 pi out front. My new integral is going to run from 0 to pi. This x times dx, this piece here, is what makes up most of my differential. 1/4 dz is equal to x dx. So the two underlined pieces here will make 1/4 of dz. And then the sine of 2x squared is the sine of z. So this will be the sine of z times 1/4 dz. Is everybody comfortable with that substitution? Let's take a minute there and make sure we're all good. I can pop out the 1/4, 12 pi becomes 3 pi. Sine of z, when you integrate that, becomes negative cos of z. And we evaluate between 0 and pi. The negative cos z between 0 and pi, that's the same evaluation that we did last time. That's just 2. Right? At the upper bound, you get negative, -1. At the lower bound, you get negative, +1. But you're subtracting, so it'll be 6 pi altogether, because this piece, when you evaluate, you get 2. Okay. I know that officially this is the end of class time, but I want to do at least one more example using the cylindrical shells method. So if you have to go, you have to go, I understand. But if you can hang around, please hang around with me for just one more minute. All right, my next class starts in 10 minutes, but I would really like to show you guys at least one more example. This one is really the same example that we did last time, just with some extra numbers thrown in. So if you want to go back and pause that, watch it more slowly, you're welcome to, but let me grab just one more. 12 is the torus. I'll give you a hint. Don't do this with cylindrical shells. The cylindrical shells on this, go ahead and set up the integral. But this requires, if you want to see how to handle the cylindrical shells integral here, if you're stuck on that, you can come see me in office hours. It's a pretty tough integral. It requires some clever stuff. But if you think of this as a slicing problem, it becomes much nicer. So imagine your axis is running straight around the torus in the middle, and you'll find a nicer way to do that. Let me take a look at number 11 really quick. Now let's look at 10. 10 will be faster. So got y equals 5 times the cube root of x, y equals 0, y equals 1, and we're going about the y-axis. Five times the cube root of x looks a lot like the cube root of x. It's just been stretched vertically by a factor of 5. So he looks like this over here, like this over here. Y equals 0, that's the x-axis. Y equals 1, we'll call that right here. So here is my region, and I want to rotate about the y-axis. So I'll draw my strip in parallel to the axis of rotation, like this. And this is another case where I would probably go back and redraw my graph, giving me zooming in on this portion. But we can proceed here. the point along the curve where the strip interacts there, that's x comma 5 cube roots of x. If I rotate just that strip, then I'll get a cylindrical shell whose radius is this and whose height is this. So r again here is just going to be x, but h is a little bit novel now. The height of this strip is this y value minus this y value. The y value up here is 1. And the y value here is 5 cube roots of x. What's that, sweetie? Okay. So let me go ahead and zoom in on that region just for a second. And here's my strip. This is x comma 5 cube roots x. And this up here is y equals 1. So the height of my strip, this guy, is this y value minus this y value. The y value here is 1, and the y value here is 5 cube roots of x. So I hope that helps you see why h is what it is. So then your dv is 2 pi r h, and in this case, a thickness of my strip is dx. So that's 2 pi times x times 1 minus 5 times the cube root of x dx. And then the last thing I'll do here is just write down what the actual volume integral is. I won't finish it because I know we are over time. V will be the integral of dv taken from the smallest x value in my region up to the largest x value in my region. To find the largest x value in my region, I have to ask when is this equal to 1? All right, so I would need to find this intersection point. I would set 1 equal to 5 times the cube root of x. That would mean 1/5 is equal to the cube root of x. And then if I cube both sides, that will tell me x is 1 over 125, right? 5 cubed is 125. So I would be integrating from 0, x equals 0 over here, to 1 over 125. And then my integrand is 2 pi x times 1 minus 5 cube roots of x dx. So I know we didn't get a lot of time to do extra practice with these cylindrical shells. It turned out most of the questions you guys wanted to look at were still disk washer questions, which makes me suspect that probably we haven't gotten all the way into the cylindrical shells part of the homework. That's not the end of the world, but I want to advise you, please work hard on that homework. And as you run into bits there which give you trouble, come look at these examples. All right, so there's lots and lots of good examples here. I've got several videos of Patrick JMT solving problems just like this. Those will be helpful. Try to visualize the strips, and if you're having trouble seeing how that connects to the solid overall, look at these 2 videos. And that is where we're going to have to leave it for today. So please work hard on these. If you have questions, you can come by my office hours, or you can send me a Canvas message, of course. And that is it, ladies and gents. I will see you, I guess not Monday, because that's Labor Day, but Wednesday of next week. Take care.